I'm Lerner with LPPFusion, and welcome to the second episode of JWST and the Big Bang Never Happened debate. In this episode, we're going to be discussing the scientific method and the method of Big Bang cosmology. Well, many of you who have been watching this debate know that Brian Keating and others have continued to respond to my article in these videos. Unfortunately, so far they haven't actually responded to my actual scientific, technical arguments or the specific questions that I posed in the last video. But for this video, we're going to put aside those technical arguments and look at the non-technical arguments that have been put forward against our point of view, because that sheds light on the method questions, which are very important. So, most of you have seen that one of the most common comments on the controversy is people will say, oh, don't pay attention to what Eric Lerner is saying. He's been saying that for 30 years, ever since he published the book, The Big Bang Never Happened. Why, it even had the same title as the article, almost. So, in essence, they're saying that I've been putting forward, and my colleagues have been putting forward, theories that haven't needed changing for 30 years because they've actually fit the observations. And that's a bad thing. I mean, what would these people say if Maxwell was still alive? Oh, you're still spouting those same four equations? I mean, people are putting those on t-shirts, for God's sake. Or Newton. 400 years and it's still force equals mass times acceleration, F equals ma. I mean, Sir Isaac, how old hat can you get? What's the strength of science? What's the usefulness of science? Is that we can formulate general laws that can remain fixed and can predict a whole range of phenomena that we haven't observed before. And that allows us to develop technologies based on these theories that are reliable. And yet, this isn't the method that the Big Bang cosmologists are using. Dr. Becky and Brian and others have actually described this method. They've said it's not a bad thing that we're surprised by the JWST results, because that's our method. We put forward our theories, which are based on, exactly calculated mathematical assumptions. And then we get in new observations. We look at the observations, and then we tweak the theories. They always seem to like to use that word, tweaking. We tweak the theories so that they explain the observations we've made. And when new observations come in, well, of course, we have to tweak the theory again to make it up to date to fit the new observations. Add a little dark energy here, a little dark matter there, a little inflation. And that's how the theory goes. Well, that is an accurate description of the method of Big Bang cosmology, but it is not the scientific method. The scientific method that's brought us all of these great technologies over the last several hundred years, antibiotics, space travel, computers, electricity. That's a different method. What's left out of the description of the tweaking method are two important characteristics of the scientific method. One is the importance of predictions, and the other is the use of predictions to eliminate, to reject wrong theories. If a theory is consistently wrong in predicting observations, then it has to be rejected. This isn't just, my description of the scientific method. This is what was developed hundreds of years ago during the scientific revolution. Let's take as an authority Leonardo da Vinci, quoting from my own book, A Reliable Source. So Leonardo writes, "We must consult experience in the variety of cases and circumstances until we can draw from them a general rule that is contained in them. And for what purposes are these rules good? They lead us to further investigations of nature and to creations of art." And by this he means not just artistic creations, but the creations of invention of what we would call technology. They prevent us from deceiving ourselves and others by promising results that are not obtainable. In other words, a good rule eliminates bad predictions. The approach of Big Bang cosmology, as Alfvén noted decades ago, is a throwback to an earlier method, the Ptolemaic method. You remember Ptolemy. He's the one with the geocentric universe and the epicycles. And that Ptolemaic method was indeed starting from exact mathematical assumptions. His case, that the Earth was the center of the solar system and that the planets and the sun and the moon moved in perfect circles. Look at the observations and then tweak the theory to fit the observations. In his example with epicycles. This was the method that was overthrown during the course of the scientific revolution. Now, it wasn't overthrown with Copernicus. Copernicus actually was preserving as best he could the idea of these perfect circles, even in a heliocentric model of the solar system. It was really in the next century with Kepler and then Galileo that this whole method was overthrown, based on earlier work by Leonardo and going back to hundreds of years to the work of Arab scientists. Kepler was actually initially working within this same Ptolemaic methodology. He had inherited the notebooks of Tycho Brahe. And Tycho Brahe had developed extremely precise instruments, even though they were used with the naked eye, that he could use to observe the planets. So his instruments were sort of the JWST of 400 years ago. Tycho Brahe's observations, even though made with the naked eye, were 100 times more accurate than Ptolemy's ancient ones. Well, Kepler worked for years with these observations and tried to tweak the perfect circle theory with very sophisticated mathematics, with the mathematics of perfect solid forms developed in antiquity. But, and here was Kepler's real brilliance, after all this work, he realized that the theory could not predict new observations. So he rejected that theory, which had stood not for decades, but for centuries. And he made the brilliant deduction that the orbits of the planets were not circles, but ellipses with the sun at one focus. And they did not move at a constant rate, but they moved at a rate which swept out equal areas in equal times. He formulated Kepler's laws of motion, which could fit not only Tycho Brahe's observations, but fit observations that were made for decades later. Now, he didn't explain why Kepler's laws were valid. It took a whole lifetime until the end of the 1600s when Newton was able to derive Kepler's laws from the universal law of gravitation, the m/r² formula. But what happened was he used the observations to reject a theory and to formulate a theory whose predictions worked. Well, we use the same theory when we added to our non-Big Bang explanations of cosmic evolution. We didn't actually have to revise any of the theories that were developed in the 80s and the 90s, and that's true. But we did expand the theory almost 20 years ago. If you read my book, The Big Bang Never Happened, I'm quite agnostic on what is the cause of the Hubble relationship between redshift and distance. In fact, I put a whole appendix on the various theories, because you could have an expanding universe with no Big Bang. You could have, as Alfvén hypothesized, galaxies moving through the universe without space expanding at all. Or you could have, as Vigier and others hypothesized, a tired light hypothesis, that the redshift was due to something that happened to light as it traveled long distances. I didn't reach any conclusions. All the hypotheses had problems, but the data wasn't really there. And I didn't mention the Tolman test anywhere in my book either, because again, the data to test the Tolman hypothesis at large redshifts didn't exist in the 20th century. But in 2004, things changed. The Hubble Ultra Deep Field was able to probe galaxies out to high redshifts, to a redshift of 5, almost 6. When I read those observations on galaxy size, a paper by a scientist named Booens and his collaborators, well, it didn't take Kepler's brilliance to notice that they followed the very simple formula, 1 over z. Theta equals 1 over z. The angular size observationally decreased with increase in redshift. One was inversely proportional to the other. Well, as soon as I saw this observation and derived this very simple rule, I realized that that implied that the universe was not expanding, that the Hubble redshift could not come from expansion either in space or of space, and that distance must be linearly proportional to redshift. Very simple algebraic conclusion. Well, I tested this hypothesis on a different set of data. I said, well, we can derive what the apparent magnitudes, the apparent brightness of the supernova should be if the universe is not expanding and redshift is proportional to distance. Well, I found that it was a perfect fit to the data. In fact, mathematically, it's almost impossible to distinguish up to a redshift of 5 between the simple formula derived from the non-expanding universe and the very complex formula that is derived on the basis of expansion, dark energy, and dark matter. So as soon as I saw that a separate set of data that wasn't used to derive this rule could be predicted from this rule using the scientific method developed by Leonardo, Kepler, and others, it was easy to see that this was the right answer. And I and my colleagues, Ricardo Scarpa and Renato Filamo, did very careful studies on thousands of galaxies as the data poured in to show that this hypothesis correctly predicted new observations. So we were able, after many years of effort, to get these results published in peer-reviewed journals, including the monthly notices of the Royal Astronomical Society. And since they went up to a redshift of 5, we really weren't making a big stretch to predict that at a redshift of 10 or 12, what JWST has already reached, the same predictions would be valid, that the universe was not expanding and that distance and redshift were proportional. So this is an example of the way the scientific method uses predictions to test hypotheses, in this case, the non-expanding hypothesis. But that's not what Big Bang cosmologists do. It's not just me that says there are 16 separate data sets where the Big Bang hypotheses are wrong. You can read papers published with hundreds of authors to a single paper, listing 24 different ways the predictions of the Big Bang theory don't match observations. But the difference is they don't conclude from that the Big Bang hypothesis should be rejected. They simply say, these are anomalies. As Dr. Becky would say, the theory needs some more tweaking. And they even list something like a dozen or 2 dozen different varieties of dark energy that perhaps could be used to tweak the theory. Fuzzy dark energy, early dark energy, late dark energy, darker dark energy. Now, to see what's wrong with this idea that predictions aren't used to reject a theory, let's think of an example in which the Big Bang theorists are running an airline. You go up to the Big Bang window and you ask for an airline ticket. Because you're not familiar with this airline, you ask what their safety record is. And they say, well, in the last 17 flights across the Atlantic, our planes have crashed 16 times, and they've gotten across once. The Big Bang theory, the one good prediction they made was of deuterium abundance. So you say, so your plane crashed 16 times and only got across once. In other words, your predictions that the plane would get across were wrong. The guy says, well, yeah, that's true, but after each crash, we tweaked our design and we were able to explain exactly why the crash occurred. And then we flew the plane again. You say, but the plane crashed again. Well, then we tweaked the theory again. Well, Dr. Becky, Brian, gang, dear viewer, would you buy that ticket on that airline? Would you fly the airline whose predictions of getting across the Atlantic were so wrong? Well, if the answer is no, and I'm sure it is, why do you stick with the Big Bang theory, which has so many wrong predictions? Of course, people will say, well, that's a foolish analogy. They're talking about cosmology, not flying across the Atlantic. There's no real-world consequences if their predictions are wrong. Cosmology has nothing to do with real-world technology. And that's, again, where Big Bang cosmology has become a throwback to the Ptolemaic method. In the Ptolemaic method, the cosmos, the heavens, was completely separate from the Earth. The Earth was, well, the Earth. Decayed, evil, violent. This was the Middle Ages, after all. Now, the heavens were perfect. Everything moved in perfect circle at the same rate. The scientific revolution destroyed that distinction. The apocryphal tale of Newton and the apple symbolizes a real insight that the scientists of the early scientific revolution had, which is that the same physical laws that govern on Earth govern the cosmos. So we can learn from the cosmos how things can be done on Earth. We can apply those lessons to technology. And that was actually done, although it took a long time. One of the things that you could learn, if you could correctly predict where the moon and the planets would be in the sky, is where you are. How can this be done? Well, if you can predict exactly where on the sky the moon is at any given moment, you can publish those tables accurately based on Newton's theory of gravitation, and you've got a clock in the sky. You can know what time it is in Greenwich, England, simply by carefully measuring with instruments you can carry and use on a rocking sailing ship where the moon is in the sky. And if the next day you measure what time the sun reaches its highest point, which is your local noon, then you can easily calculate what your longitude is. The ancients had known you can calculate your latitude by simply sighting and measuring the height of the star Polaris. So if you know your latitude and your longitude, you know where you are on the ocean, which was very, very valuable information if you wanted to safely get across the ocean. So the discoveries of the cosmos had real-world consequences, and they have ever since. I'm doing research in fusion energy, and the very existence of fusion reactions was discovered by studies in how the sun produced its energy. It was Hans Bethe in the 1930s that, on the basis of what was known of nuclear reactions and the E=mc² formula, he deduced the fusion reactions that must be occurring in the sun and other stars to produce the vast amounts of energy that had never before been explained. So the heavens, the cosmos, has consequences here on Earth. But that relationship was broken with Big Bang cosmology. Big Bang cosmology started to hypothesize, especially going forward from the 1980s, entities like inflation, dark energy, that not only were not observed on Earth, they could not be observed on Earth. And the cosmos again became the realm of perfect mathematical theories. And you'll see in some of these videos that people say the expansion of the universe, something in the real universe, can simply be mathematically derived from general relativity, a mathematical theory. Well, that's simply not true. In fact, as Einstein himself said, you can only get this conclusion if you make a hypothesis about the real universe. And that hypothesis is that the universe is completely uniform at the largest scales. A hypothesis that was not borne out by observation in Einstein's time and has not been borne out at any scale by observations today. The universe is, in fact, inhomogeneous, lumpy, at all scales, and that invalidates the prediction of getting expansion from general relativity. But the key thing, again, is methodological, that the advocates of Big Bang cosmology are trying to break the relationship between the cosmos and what happens on Earth, between theoretical physics and technology.